Welcome to the chapter 11 of the Oil and Gas Engineering audiobook. This chapter presents the work and the deliverables of the Instrumentation and Control discipline, also called Instrumentation and Automation discipline. The scope of this discipline is to specify all the field instruments and to specify all the plant systems, including, for instance, the process control system, as well as the emergency shutdown system, fire and gas system, and the other systems.
The starting point of the discipline is the P&IDs. On the P&IDs, process has shown all instruments required for monitoring, control, and shutdown. For monitoring, process also specified if the measurement shall be locally available or available remotely from the control room. There are two types of instruments. Field instruments, which are depicted on the P&ID by means of a circle, such as this pressure indicator, and virtual, also called soft instruments, which are displays on control systems screens or signals inside systems. These instruments are depicted on the P&IDs with a square frame. So this pressure indication, for instance, is available on the screen of the control system remotely from the control room, whereas this pressure indication is only available locally. This symbology is international. It is the International Society of Automation, ISA, symbology. So, instruments with a circle, local instruments. Instruments with a square frame, available on the operator display remotely in the control room. The instrument engineer first task is to produce the list of all instruments specified by process on the P&IDs. This forms the instruments list or instruments database. This is a central document for the Instrumentation and Automation discipline. It will indeed list all the field instruments that required to be specified, as well as all the list of IOs, input and output, for the systems. So it will also give the capacity of these systems. Once the instrument list has been produced, each field instrument must be specified. A datasheet is produced to this end. As we have seen, a process datasheet has already been issued for some instruments such as control valves, pressure safety relief valves, flow instrument. For the other instruments, the process information is available on the heat and mass balance. The process datasheet of a control valve, for instance, shows the functional requirements, which is the operating range, so the extreme operating cases, as well as the maximum differential pressure for sizing of the actuator and the fail-safe position. Instrumentation discipline complements this information, this process information, with mechanical as well as electrical and instrumentation information. It produces the instrument datasheet, also called instrument mechanical datasheet. It shows for the body the types of materials to be used for the body and the trim, the type of end connections, and such information is specified by piping. So instrumentation gets this information from piping. It also specifies the type of actuator as well as the type of positioner and the type of signals that will be exchanged between the instrument and the control system.
As stated in introduction, another work stream of this discipline are the systems. First of all, the process control system. The process control system functionalities are entirely defined by process. They are defined by means of two documents. First of all, the PNIDs, which shows the process controllers, as well as all the instruments that are part of the process control system, as well as control narrative or functional analysis, which are issued to explain in more details the control functions that shall be implemented in the process control system. The application software of the process control system is developed based on these two documents. Besides the process control system, another system is in charge of the safety of the process. It is the process safety system, also called emergency shutdown system, also called safety instrumented system. The process control system and process safety system have completely different equipment. They use different sensors, different controllers, and different final elements. For instance, in this particular system, the liquid level at the bottom of this column is controlled by this controller, which is part of the process control system, as it is shown with a circle, which acts on this level control valve to maintain a particular level in this column. Now, should this controller fail, or this valve fail, and the level fall too low, this sensor, level transmitter, will pick it up and send a signal to the process shutdown system, which will close this shutdown valve to avoid that the liquid level will fall down and gas will blow by to the downstream system. As you see, the process control system instruments, shown here in blue, and the process shutdown system instruments, shown in red, are different instruments. Each system has its own instruments as well as controllers. This is in order that the process shutdown system is a protection in case of failure of the process control system. They don't share any instruments, so the process shutdown system acts as a backup for the failure of the process control system. As the process safety system performs safety functions, it requires a high level of reliability, and the corresponding controllers are either duplicated or triplicated, i.e., instead of one controller, there will be 3 controllers, so that if one fails, the other 2 will detect the failure and will take over and implement the action. In fact, each safety instrumented function, such as the one we have seen here, very low level closes the valve, is subject to an audit. The purpose of this audit is to identify how critical this safety instrumented function, so the one that detects a very low level and closes this shutdown valve, is, how critical it is. And for this, the consequence of the failure of the control valve that requires this safety instrumented function to operate is assessed. So the risk linked to the malfunction of this level control valve is assessed by identifying, first of all, its likelihood, and then the severity of the consequences. The product of the two is the risk level. If the risk level falls in the non-tolerable risk area, i.e. high likelihood and severe consequences, then it shall not be allowed. So safeguard, the instrumented safeguard that is designed to prevent it, is specified a high reliability level, which means a seal level. If the failure of this control valve, well, the product of the likelihood and consequence of failure is in the tolerable risk area, then this safety instrumented function is not specified a safety integrity level, which is the case for the majority of safety instrumented function. If the safety instrumented function is specified a seal rating, then it will be subject in a second step to a thorough review of the type of equipment, such as the sensor, the controllers, and the final element, and their probability of failure, so that the overall loop, the overall instrumented safeguard, provides the adequate probability of failure on demand. This is called the seal review. Each of these systems, the process control system and process safety system or safety instrumented system, comprises field instruments, controllers, as well as operator consoles. In order to minimize the cable lengths between field instruments and controllers, these controllers are located next to the units in instrumentation equipment rooms. So there are several instrumentation buildings throughout the plant housing these instrumentation equipment rooms and system cabinets for both the process control and the process shutdown systems. The connection between the cabinets and the central control room is by fiber optic cables. Such architecture is called a distributed architecture. This is why these systems are called distributed systems. At this stage, we have seen the majority of equipment for what concerns systems: the process control system and the process shutdown system. We must add to that some unit control system, which are control systems for specific equipment or packages. Indeed, some packaged equipment and some packaged units, such as the one shown here, are controlled by the plant systems. Their instrumentation is connected to the plant process control system and plant process safety system. Others have their own control and safety systems. This is, for instance, the case where a complex control or sequence and safety functions is required. In this case, only a few signals are exchanged between the unit control system and the plant systems. The advantage of the scheme shown here with a unit control system is that the vendor of the packaged equipment or packaged unit is entirely responsible for the design, programming, and testing of the unit control system. This is the case, for instance, for critical equipment such as turbo machinery. For such types of equipment, the unit control system is always supplied by the vendor for the reason of the responsibility. This allows to show on the architecture drawing the unit control systems of equipment. We must now introduce the fourth and last type of cabinets, which we find in the instrumentation equipment rooms, which is the fire and gas cabinet. So we have four types of cabinets: process control system, safety instrumented system, the equipment unit control systems, and the fire and gas cabinets. The fire and gas system is defined by safety, as we have seen. Safety defines the number and location of fire and gas detectors, as well as their logic of operation, shown on the cause and effect. And the system is purchased and programmed according to these two documents. There are other systems in an oil and gas facility. It includes machinery vibration monitoring system, such as the one shown here, burner management system, compressor anti-surge system, analyzers data acquisition systems, and various other types of systems. This synoptic shows all instrumentation and automation hardware, including the instruments connected to the process lines, the secondary cable or unit cable, one pair cable connection of the instruments to junction boxes, the connection of the junction boxes by means of a multi-core cable to the marshalling cabinet in the instrumentation equipment room, as well as the fiber optic connection from the instrumentation equipment rooms to the control room. Drawings must be issued by what is called installation, part of the discipline, for installing all these various bits of hardware. This starts by the allocation of field instruments to junction boxes and definition of the main cable routing. Allocation of instruments to junction boxes can be done once the PNIDs and plot plan have been finalized. The allocation is done by type of signals. There are some junction boxes for analog signals and some others for digital signals. And also, there are junction boxes for the process control system and some others for the process shutdown system. The allocation of instruments to junction boxes allows to specify the specific type of hardware that will be required for the control system. This specific hardware are the field marshalling cabinets. These cabinets indeed have terminals that mirror the ones of the junction boxes. So once the allocation of instruments to junction boxes has been done, then the marshalling cabinets can be designed and manufactured. This is actually a major progress step for the supply of the control system. And as we have seen, the allocation of instruments to junction boxes requires
the IFC PNIDs and plot plan. Hence, to reach the major progress step, at which point the field marshalling cabinets of the system can be manufactured, one needs to have the IFC PNIDs and plot plan. In fact, drawings need to be produced to install all the hardware shown on this drawing, from left to right. Let's start with the left, the instrument connection to the process line. For this connection, hookup drawings are produced, which shows the way the instrument is connected by means of tubing as well as isolation and bleed valves. The corresponding hookup material is shown on the hookup drawing. The location of the instrument and the routing of the secondary cable up to the junction box is shown on the instrument location and secondary cable routing drawing. Together with the cable list, it will allow to install the secondary cable as well as the instrument, which could be located quite far away from the tapping point. Hence, it is necessary to specify its location. The junction box wiring diagram shows the connections between secondary and multi cables. The equipment arrangement drawing shows the layout of the instrumentation equipment room, the position of the various cabinets. Finally, the instrument loop diagram shows the complete connections for one particular instrument, including numbering of terminals, cables, I/O cards, and so on. This drawing is used for pre-commissioning to test the functionality of the instrument and during troubleshooting. This concludes this